Good morning. Today we are going to finish with the lesson 2. So the remaining point is the generalized forwarding and SDN, software-defined networking. The difference between SDN and traditional IP networks are basically the independence between the control plane and data plane, because they are separated in a SDN network. If you remember the traditional IP network, for example, with this graph, we have 5 nodes with several links connecting them. In traditional IP, if a router receives one packet, for example, with a specific destination IP address, the process is as follows. I check the destination IP address, and I check my routing table, and I decide to use this outgoing port, for example. So we are only focusing on a specific field from the IP header. Moreover, there is no difference between the data plane and control plane in terms of where are they implemented. So both planes are implemented on each node, so they are not separated. The routing algorithms are distributed. The nodes have to exchange information with the neighbors and save which is the current state of the topology. Instead, if we have an SDN network, we have the same topology, right? A mesh topology, for example. And in this case, we have SDN. There is a remote controller which is connected to each of the nodes in the network. This element has a global view of the network and is in charge of saying, okay, which is the content on your flow tables. Okay, so in this case, there is a separation between the data plane and the control plane. Okay. Moreover, in the case of traditional IP networks, we only work with one field, destination IP address. In SDN, we can play with several fields from several layers, so we can do a specific match, and we can play with different actions. In IP, we only have forward to the next hop, but in this case, the actions can be drop the packet if we want to discard it, forward as well, or send to the controller because I don't know what to do with it. This is the scheme of SDN, generalized forwarding. Here we have the network topology, and we can see the separation between control plane and data plane. So on the data plane, we have the different nodes with the flow table. So now we can see that there is a difference between the forwarding table or flow table of an SDN node compared with a traditional IP network. Another difference is this one. For example, imagine that the first router receives a packet with this information. So here we have 2 fields instead of one, the destination IP address from IP traditional networks. And based on this match, we call it match, 2 fields, we can do an action. So the match is the first column headers. The action is what to do after matching. In this case, it is only forward through outgoing port number 2. But there is an important third column called counters. Once we have a rule inside a forwarding table, if traffic is injected into the network, this rule, for example, is matched, we can count how many packets, how many bytes have matched a specific matching pattern. Okay, so in this way we can know which is the situation of the network, how many packets are flowing through a specific path, and try to improve the performance of the network. So on the control plane we have the controller. This is a logically centralized device who is in charge on having first the full knowledge of the network and then install the rules. He's in charge of installing the rules according to a specific policies. In SDN we are going to talk about flows as in case of IPv6. So a flow is a succession of related packets originated from a specific source or sourced IP network or SDN network, destined to a specific destination. So in the generalized forwarding, we have the match, the combination of fields, for example, all the packets created on a specific network, destined to a specific network with this destination port or with this source MAC address, so different values. So the actions can be drop if we want to work with firewalls, discard all the packets coming from a specific device or network. Forward, which is the normal action. Modify, for example, a field in the packet, as in the case of TTL, when a packet arrives to a router, the router decides to modify the TTL field, so it is more or less the same case. Or finally, send the packet to the controller. Imagine the situation where all the flow tables are empty and the nodes do not know how to do with an incoming packet. So the flow tables are empty and they have to ask the controller what to do. I don't know what to do with this type of packet. What can I do, controller? And the controller will say, okay, install this rule and forward it to, for example, next hop by means of outgoing port number 3. As in the case of traditional routing in IP, we have priority. So the routing table or the forwarding table, in this case, flow table, has 3 columns, and the priority is in descending order. Okay, so the first rule will have the biggest or the highest priority. Then, if it is not matched, we pass to the second, and so on and so forth. Finally, the counters. The counters will let the controller know how the network is behaving. So it will have a biggest knowledge about what to do with the routing, if it is necessary to change the routing or to do some other operations to improve the performance of the network. So here we have an example. We have a specific SDN node, and we have a flow table with these 3 rules. The first one, so the priority is in descending order. The first rule refers to if I receive a packet from a source network, 1, 2, wildcard means any value, as we saw in the routing table in IP networks. The wildcard means, okay, I don't care about the specific host that generated the packet, but the source network. If this packet was generated there and destined to any host in network 3, 4, 5, drop it. We are doing a kind of firewall. We are blocking incoming traffic. Another rule could be the number 2. I don't care about the source of this packet. Would like to know is if they are destined to this specific network, forward using port 2. So I would like to use the normal destination based routing. Another potential rule could be if a packet is created by this specific host and destined to wherever, I don't know what to do, send to the controller. Okay, these are 3 different types of rules. So we have an entry on the flow table entry, and these are the different parts of the flow table entry. Okay, this is the flow table entry. We have the match. The match can be created by means of using several different fields. For example, these fields belong to the link layer, virtual LAN ID, source and destination MACs, Ethernet type. If we move to the upper layer, we have 3 different fields to be used: source and destination IP addresses and IP protocol. And finally, we can also play with the TCP source and destination port. So we can combine several of these fields and we can create a specific match for our flow table entry. You can see that here we have the switch port, the incoming port. So if we receive the packet from a specific port and this is the match, we can do the actions. Which kind of actions? These ones. We can forward the packet to a specific port. This is a normal action. As to the controller, I don't know what to do with this specific packet or match. Please help me. Drop the packet by, for example, using a kind of firewall, or send to the normal processing pipeline, because there could be some different tables inside a flow node. And modify the fields. For example, in the case of NAT, we can modify the IP addresses of the ports. The third column or part of an entry is the stats. So once we have the match, once we have injected traffic into the network, we can see how many packets, how many bytes performing the match. So in order to let the controller know how the network is behaving, which is the type of traffic, which is the link load, and act accordingly. So in this slide we have different examples of match plus actions. So in this first example we have the normal destination based forwarding. We can see, okay, all the packets destined to this specific host with this specific IP address, they should be forwarding by means of port 6. Another example, a firewall. In order to block some traffic, I would like to block all the packets that will have destination port, TCP destination port number 22. So I'm blocking all the incoming SSH traffic. This is not forward, this is a type of action, as well as this, so there's a typo here. The idea is to block some traffic, for example, originated by a specific host. Again, the drop. Another type of destination based on layer 2. Instead of working with IP addresses, we can work with source MAC addresses or destination MAC addresses. The idea is to forward to by means of a specific port. So in a controller, we can create some specific algorithms to fill up the flow tables. For example, to act like a router, the normal destination IP routing, the match is the longest destination IP prefix and forward the packet. We can do the same but layer 2, destination MAC addresses, we can forward or flood, which means that send the packets through all the ports except the one that was received from the previous hop. firewall, block traffic, permit or deny, or not, modify some of the ports, some of the fields, IPs and ports for the translation from private to public IP addresses. Finally, I'm going to show you an example. The idea is to fill up all the flow tables of the 3 switches in the scenario. We have a scenario with 3 switches, 6 hosts connected in this way, and 1 controller. Okay, so the example says that datagrams from host 5 and 6 should be sent to H3 or H4 via S1 and from there to S2. So this is the path that must be followed. We are specifying a unique path from S3 to S1, from S1 to S2. So we have to create the 3 flow tables on S3, S1, and S2. And this is the result. S3 has this flow table. All the packets created on this network is 10, 3, wildcard, and they are sent to this network, which prefix 10 to wildcard must be forwarding using this path, outgoing port number 3. Okay, so this is the content of the flow table of S3. Let's move to the next flow table, S1. So first of all, I receive the packet by means of this incoming port. Then the source is the same, the red network, and the destination is the same, the green one. So forward by means of this outgoing port, number 4. This is the content of the flow table of S1. Finally, I receive the packet from the incoming port number 2. So I have to distinguish, are they destined to host 3 or host 4? This is the reason why I need 2 entries. So this flow table has 2 entries, one for host 3, this one, and the other one for host 4, this one. Okay, so the ingress port and destination traffic is this one. We can forward my means, so this link or this link. Okay, so before finishing, I would like to ask you another example, another exercise that will be corrected on the next class. So the idea is that datagrams from host 5 and this time to network 10 to wildcard, 10 to wildcard, so be sent through link S3 to S1, so this link. But datagrams from this host H6 destined to the same network should follow this path. So in this case, we are working with load balancing. The first question is it possible to do load balancing by means of traditional IP routing? I will give I will like to hear your explanation to this question, and then to solve this problem on the next class. So finally, we have finished with lesson 2, the data plane on the IP protocol. We have seen IPv4, IPv6, fragmentation, the datagram format for both protocols, the addressing, the subnetting, the NATing, and finally the generalized forwarding and SDN. Okay, so thank you and talk to you soon.